Have you ever stood in an elevator, listening to the hum as it climbs, and had that tiny, fleeting thought, what if? Well, today we're going to look right into that moment. We're pulling back the curtain on the hidden physics of an emergency stop, and we're doing it with a fantastic, in-depth analysis from the experts at Novin Pooya Elevator.
So let's just get right into it. The worst happens. The car starts moving too fast. In that one split second, what actually happens? What are the unseen forces that are unleashed to save you from a free fall? Because, it's not some kind of magic that brings that car to a stop. What's really going on is a brutal, high-stakes battle of physics. And frankly, the outcome of that battle decides your fate.
To really understand this fight, first we've got to meet the main opponent, this absolutely colossal force that just appears out of thin air the second those emergency brakes kick in.
That force is called inertial force. You can think of it as the ghost in the machine. It's the powerful, stubborn refusal of that heavy elevator car and everyone inside to stop moving. It wants to keep going down, even while the brakes are desperately trying to clamp on and stop it.
And the scale of this force, it's just staggering. The Novin Pooya analysis actually calculates that a standard 2-ton elevator in an emergency stop generates a downward force of roughly 4 tons. Okay, to put that in perspective, that's like having 2 rhinos suddenly trying to rip the elevator car straight through its own safety brakes.
So how in the world do you fight a 4-ton ghost? Well, you're going to need a hero. And in this story, our hero is this incredible mechanical marvel called the safety gear system. And this thing acts with lightning speed through this perfect chain of command. It's amazing. First, a device called an overspeed governor senses something is wrong. It's moving too fast. It instantly locks a special rope. That locked rope immediately yanks a lever under the car, which activates the safety gear. And finally, bam! Powerful jaws slam onto the steel guide rails, grinding the car to a complete stop. It all happens in a blink.
But here's the thing. Not all brakes are made the same. You've basically got 2 kinds. There's the older, instantaneous type, which is exactly what it sounds like. It's like hitting a brick wall. A super violent, jarring stop that's only used in really slow elevators. But all modern, high-speed elevators, they use a progressive system. This is way smarter. It's more like a controlled, powerful skid, applying the braking force firmly but smoothly. It's a much, much safer stop that dramatically reduces the impact on you and the elevator itself.
But even with the absolute best brakes, remember that 4-ton force we talked about? All that energy has to go somewhere, and where it goes is straight into the steel backbone of the elevator shaft, the guide rails. And the results of that energy transfer can be pretty brutal. We're talking deep grooves gouged into the steel, rails getting bent out of shape, sometimes even permanent deformation. Over time, this kind of stress can lead to fatigue cracks, or in the absolute worst-case scenario, a catastrophic failure where the rail itself just fractures.
And this is where it gets kind of crazy. It's a total paradox. The very system that's designed to be your absolute last line of defense can become its own worst enemy, causing massive structural damage just in the act of saving you if it's not engineered perfectly. So how do you stop that from happening? How do you actually design a system that can win this battle every single time without destroying itself? Well, this is where the engineering, as detailed by Novin Pooya, gets really, really impressive.
First, you got to understand what makes the force worse. Yeah, mass is a factor, of course. A heavier car equals more force. The type of brake matters a ton, as we saw. But the undisputed king here is speed. It's not even close. A little more speed doesn't just mean a little more force, it means a lot more force. Speed is the biggest danger by far. So, the solution starts with choosing the right weapon for the fight, and that's the guide rail itself. It's not a one-size-fits-all thing. For taller buildings, for faster elevators, for heavier loads, engineers spec out progressively stronger, beefier, and more precisely machined rail profiles like these T-series rails to handle those insane forces. But hey, even the strongest rail in the world is useless if it's not supported correctly. You have to think of it as a whole ecosystem of strength. Engineers optimize everything. They put the support brackets closer together to make the rails stiffer, they use high-strength steel for the brackets themselves, and they make sure those brackets are anchored to the building with incredible precision. We're talking laser-guided alignment, so there are no weak spots. So when you put all of that together, it just completely changes how you see the inside of an elevator shaft. You realize those simple-looking steel tracks running up the wall, there's so much more than just a track.
I think the Novin Pooya elevator analysis just says it perfectly. Guide rails are not just a path of motion, but the backbone of safety in the final moment.
That's what they are. They are the unsung heroes of the elevator. They are a testament to this incredible, invisible, robust engineering that is silently at work protecting us every single day.
So the next time you step into an elevator and you hear that door slide shut, maybe you'll think about those steel rails, that hidden backbone of safety, and you might just ask yourself, will you ever ride an elevator the same way again?